So, here we go. This is in your packet, example 1. This is mostly a review of the warm-up we just did. So it says find the mean, median, but then there's 2 new words, mode and range. See if you can remember those from middle school. Find the mean, median, mode, and range for this data set, which is like world record mile running times.
No.
3.4 minute mile. Which 0.4, that's not 40 seconds, right? 3.4 would be 40% of a minute.
So
40% would be 0.4, right? Of a minute is 24 seconds. So 3 minute, 24 second mile. Anyone do that? Not real sure where they got this data from. Alright, go ahead and find those 4 things. If you're watching the video, you can pause it and find those.
Number. Yeah. The range, the highest number minus the smallest number. Make something good. Hey, if later, but yeah, he definitely.
For the mean, add them all up, divide by 6, I got 3.9.
Yep.
Whoa.
Okay? The median, now these are not in order, so let's do that real quick. So 3.4.
36, 37, 41, 41, 45.
3.6.
4.
So the median, what happens if there's an even number?
You add those.
So there's 3 numbers on the left and there's 3 numbers on the right. You add them up and you find the average of the middle 2. So 3.7 plus 4.1 divided by 2 is 3.9.
So
The mode, do it.
you add both sides?
No, just the middle.
No, the middle 2.
The middle 2, 3.7 and 4.
Yeah, so you add up the middle. It's the average of the middle 2 when the median is split between 2 numbers.
And then you divide by 2.
The average, yep.
Okay.
The mode is the one that
Most frequent.
is most frequent. Sometimes that's a useful piece of data, sometimes it's not. But the mode here would be 4.1 because that one happens twice and none of the other ones are repeated.
When would it be? Like, when is it useful and not useful?
It would be useful if you're maybe if you take a poll and the most people say they like the color red, so you're going to print more red t-shirts. It would not be useful if you're trying to center data around a number, because typically the mode is not always the mean. It's just kind of different data sets. But I'd say like something where you're advertising or something where you're selling something, a mode is usually pretty helpful because it tells you like what's most popular, what's most common. And then the range, does anyone remember what that word means?
Biggest
The lowest divided by
minus
what's
the smallest.
largest minus.
I was listening to that exam now.
The most
She
common.
said, I don't know.
Okay, the range is the largest one minus the smallest one. That's the range of numbers that are.
So there's 2 4.1.
So I got 1.1 for the range. So the range tells you like how spread out the numbers are, right? So if it's a really big range, the numbers are really spread out. If it's a really small range, they're all pretty close together.
The highest number is 4.5 minus.
All right, example 2. Have you guys seen a frequency table before?
No.
So the frequency table tells you
How frequent?
how frequent that data point was taken. So 58 degrees was measured twice. 59 degrees was measured once. So a frequency table is really easy for mode, right? What's the mode?
61.
Yeah, the one that occurred most 7 times was 61. So frequency tables and what we're going to do, I know dot plots are very helpful for mode, but we'll see some more stuff here in a second. See if you can now find these 3 other pieces of data with a frequency table. So yeah, if you can do it the old-fashioned way if you want. You can do 58 plus 58 plus 59 plus 60 plus 60 plus 60 plus 60 plus 60. Right? You could do it that way. You could also do it 2 times 58, right? Twice, plus 59, plus 5 times 60, plus 7 times 61, and so on.
I'm so confused.
It's divided by 30.
So,
Yeah. I got 61.6.
1.8.
That's what I got. So the total is 1850. Now, how could we figure out how many total numbers there were?
Add all the
Add up all the frequencies. So what did you get?
30.
Yeah, it's 30. So for the mean, we need to divide that number by 30. So about 61.67, or you could say 66 repeating. What about the median?
I did it. Anyway,
What's an easy way to maybe do the median?
I just put like tally marks in the boxes.
Okay, that works. Cool. You can kind of, if you want to list them all out, you can. What would be, so think of 30 numbers. How many would there be on each side? 15 and 15, right? Which means that there's actually going to be 2 numbers in the middle again, because it's an even number, okay? So what I like to do is I'll count up 15 from the bottom and count up 15 from the top. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this right here is the middle. Does everyone see how that, because this is 15 numbers and this is 15 numbers? So yeah, so this number and this number are the 2 numbers that are in the middle. See how I did that?
Will the
Oh,
median
that's
and
a
the
good
mode
trick.
always be pretty close to each other?
Do what?
Will the median and the mode always be close to each other?
No, the mode has nothing to do necessarily with the middle.
Not the mode, the mean.
A lot of times, yes, it tells you that the data is very centered, but we're going to see later on that that's not always the case. So what would the median be?
61.5.
Yeah, the average of the 2 in the middle. And then the range, what's the highest one minus the lowest one? 7 degrees. Technically, these are all degrees, I guess. The next thing we're going to learn about is quartiles and interquartile range. Have you heard of quartiles before?
No.
What does it sound like?
Quarter.
Quarters. It is exactly what it sounds like. So based on the picture on the board, what do you think we're going to do with the data?
In between quarters.
Yeah, we're going to split it into 4 parts, into quarters, okay? So you can kind of see that if we split data into 4 parts, how much of the data is each part? 25%, right? A quarter, a quarter, a quarter, a quarter. Okay? The middle is the median, and it says that there. The middle is always the median. The first quartile is the median of the left half. So pretend like this is just a normal data set right here. What is the middle of the first half?
3.
The number 3. So you can see 3 is the first quartile. The median we call the second quartile. And then the third quartile is the median of the second half, which would be 11. So that's how we split it into 4 parts. So there's really 3 quartiles that we talk about usually, which splits it into 4 parts, right? So let's take a look at, have you guys seen a box and whisker pot before?
No.
I know you did in middle
Yes.
school. It might have
Yes,
been a
I
while.
feel it. A what?
I don't know what they call it though.
Because it's a box and they call these whiskers.
Don't
So the box and whisker pot is exactly this. So the way they do it, the box is created by the median and the quartiles. So that's the box. And then the whiskers go down to the minimum and the maximum.
We just call it a cake.
So quartile 1, quartile 2, quartile 3 is what the box and whisker pot is showing. Why do you think the box is around the data in the middle?
That's what's important.
A lot of times that's what's important. And then the whiskers are usually not as important. But sometimes they are, sometimes they're not. So let's do a box and whisker pot with this set of data. So everyone real quick, find the actual median. So the quarter 2 is the median? It's on your paper.
You know,
That's
Mr.
probably
Stokes,
a little bit easier.
you know that if you cut off cat from the skin, it comes down the house and it falls over.
Yes.
Oh, hi.
Everyone knows that.
I don't know what happens if you put rubbing alcohol.
So they are important, okay? They are important. What you say? Rubbing alcohol.
So what's the median?
5.5.
5.5. So watch this. Down below it, I'm going to draw a line in the middle. So we just found out the median is 5.5, right? So let's see how we got that. Now, if you want, you can kind of draw a line in the data set. That helps you out too.
Probably 5.5.
It's the middle of 6, 8, 9, is 5.
Then we're going to draw a box, a rectangle. This number, so this is Q1. This is Q2. This is quarter 3. So now, what is the median of the left half? What's the median of the left half?
2.5.
2.5. And then the median of the right half is quarter 3. So median of the right half would be 7.5.
So basically, like the ends of like the boxes.
Yep.
Are like the medians
Of the halves.
yeah.
So the middle is the median of the whole set. Quarter 1 is the median of the first half. Quarter 3 is the median of the second half. Then what we do is we draw a little whisker, and this number represents the minimum, what's the lowest number? 1. And then we draw another whisker over to the other side. This represents the maximum.
So what happens if the main like?
So if they might ask you, what is, I'm going to quiz you on a few questions here. What is quartile 2? 5.5. So Q2 is the median, right? Q2 is the median, is 5.5. What is Q1?
2.5.
That's the median of the first half. What is Q3? 7.5. What's the min?
1,
The min is 1. What is the max?
10.
And then the last thing is called the interquartile range. If you had to take a wild guess, what do you think the interquartile range is asking me?
Is the range inside the box. It's 5.
It's the range from Q3 to Q1. We call these the interquartiles, the quartiles that form the box. So the range of the interquartiles would be 7.5 minus 2.5, which is what? 5. So that's the range of kind of the central data is what that's saying. Okay, I'm going to do 2 more of these. I'm going to have you do them on their own. So I'm going to give you this data set here.
Run down.
Yeah, write these down.
I'm asking you back on
Blue
the IQR side.
Say it down fast.
My toes are so cold.
Okay, find each of these things for both of these data sets. So do this one, and then do this one. I want you to find the median, which is Q2, Q1, Q3, min, max, and the interquartile range. Find each of those things for both of these data sets. If you're watching the video, go ahead and pause it and do that, and then check your answers. So on the first data set, we have an even set of numbers. We have 8 numbers. So the median would be the number between the 4th and the 5th numbers, which would be 9. So 9 would be there. What's the median of the numbers to the left of 9?
4.5.
Yeah, so the median of 2.7 would be 4.5. What's the median to the numbers to the right of 9?
16.
16. Notice we didn't use the median, right? It's the numbers to the right of the median, and it's the numbers to the left of the median. Okay? What is the min?
1.
Max?
20.
The range of the inner quartiles. So Q3 minus Q1 would be 11.5. Okay, I'll give you like one more minute to finish up number 2 if you haven't done that one yet. So quarter 2. So what happens when we have an odd number? So we have
It's easier.
do what? Yeah. So what would the median be?
9.
Yeah, the exact middle number is 9. So that is the median. Quarter 2. So once again, you don't use the median for the numbers for the quarter 1. So what is the median of the left side now? Yeah, it's even easier when it's an odd number. What is the median of the right side? 11. Min?
2.
Max?
31.
Inner quartile range is quarter 3 minus quarter 1.
8.
Easy peasy.
So I want to put this on video real quick. We just kind of talked about this. So remember, our quartiles split the data into the median, quarter 1 and quarter 2. Each set of data is a quarter, 25% of the data. So some questions that they ask you. Here's quarter 1. Quarter 2 is the median. Quarter 3. What percent of the data is less than quarter 3?
75%.
What percent of the data is greater than quarter 1?
75%.
What percent of data is less than quarter 2?
50.
Or they might say the median. They might say what percent of data is greater than the median? 50%. So, all right. It says the average mean is not always the best number to describe a data set. That's why we have all these different numbers. We have the mean, we have the median, we have the mode, they have the width, the range. It depends what you're looking for is what's most important. For example, it says if there's a gathering of 100 people, 50 of them, Cole, are 40 years old, and the other 50 are newborn babies. We'll consider them to be 0 years old or not a year old yet. Maybe it was bring your baby and we'll do baby yoga or something. I don't know. That means, what is the average age? If half are 40 and half are 0, 20.
That's
So it says, would the average age, which is 20 years old, of these people be the best number to describe the people that are in that room? No, it doesn't make sense. So I put a little silly thing up here. It says, let's say that a Justin Bieber promotional group notices that you have advertised the age of this group to be 20 years old, the average age. And they show up to sell Justin Bieber apparel or concert tickets. Are they going to be very happy?
Yes.
No, they're probably not going to sell many Justin Bieber tickets to newborns and 40-year-old men and women. So that's why it's important to know what's important for that data, and also why these other pieces of measurement are important. So the main one we're going to talk about is called standard deviation.
Oh, I know that.
Have you heard that word before?
No.
What does it sound like it might be describing?
How much?
The average it deviates.
The average deviates from like
Yeah,
Talk about
how much
So-
goes from the left to the right.
exactly. It's how much does the data deviate from the mean, okay? So do you think if we're talking about 40-year-olds and 0-year-olds, is that a big spread? Yeah, it's similar to range in some ways. It's the standard deviation would be pretty big, which tells me that a lot of the data is very spread out from the middle. So if I was a Justin Bieber promotional group or whatever it may be, if I knew that had a very large standard deviation, then that would probably tell me that there's not a lot of 20-year-olds in the room. They're probably either really old or really young. Okay, so I have. I'll get to that in just a second. I'm going to watch this little video here that kind of explains a little bit about standard deviation. Oops. Wrong one. I'm going to go back here in a minute and do this stuff. Yeah.
Hi guys.
I want to watch the video now and then
Hi Shane.
so as we watch it, you kind of know.
Tired of scrounging YouTube for math help?
Tired of scrounging YouTube for math help? That tutorguy.com has video. Have we discovered a new particle in physics?
Have we discovered a new particle in physics? Is a manufacturing process out of control? What percentage of men are taller than LeBron James? How about taller than Yao Ming? All of these questions can be answered using the concept of standard deviation.
For any set of data, the mean and standard
For any set of data,
deviation
the mean and standard deviation can be calculated.
Five people may have the
For
following
example,
amounts of money in their
5 people may have the following amounts of money in their
21,
wallets:
50, 62,
21, 50, 62, 85, and $90. The mean is $61.60, and the standard deviation is $28.01.
How much does the data vary from the average?
How much does the data vary from the
Standard
average?
deviation is a measure of spread.
Standard
That is,
deviation is a
how
measure of
spread out
spread.
a set of
That
data
is, how spread out a set
low
of data
standard
is.
deviation tells us that the
A
data
low
is
standard
closely
deviation
clustered
tells us
around
that the
the
data
mean
is
or average,
closely clustered around the
while high
mean
standard
or
deviation
average,
indicates that the
while
data
a
is
high standard
dispersed
deviation
over a wider
indicates that
range
the
of
data is
values.
dispersed over a wider range of
Standard
values.
deviation is used when the distribution
Standard
of data
deviation is used when the
approximately
distribution of data is
resembling a bell
approximately
curve.
We're going
normal,
to talk about more of that.
resembling a
Standard
bell
deviation is
curve.
commonly used to understand
Standard
whether a
deviation is
specific
commonly
data
used to
point is
understand whether a
standard
specific data
and
point is
expected,
standard
or
and
unusual and
expected,
unexpected.
or unusual and
Standard deviation
unexpected.
is represented by the lowercase
Standard
Greek
deviation
letter
is represented
sigma.
by the lowercase Greek letter
A data
sigma.
point's distance from the mean can be measured
A
by
data
the
point's
number of
distance
standard
from the mean can be
deviations that
measured
it
by
is
the
above
number
or
of
below
standard
the mean.
deviations that it is
A data
above or
point that
below
is
the
beyond a
mean.
certain number of
A
standard
data point that is
deviations from
beyond a
the mean
certain number of
represents
standard
an outcome that is
deviations from the
significantly
mean
above or
represents an
below the
outcome that
average.
is significantly above
This
or
can be
below
used to
the
determine
average.
whether a result is
This can be
statistically
used to determine
significant
whether a result is
or part of
statistically
expected
significant
variation.
or part of
Such as whether a
expected
bottle with an
variation,
extra ounce of soda
such as
is
whether
to
a
be
bottle with an
expected
extra ounce of
or
soda
warrants
is to
further
be expected
investigation into the
or
production
warrants
line.
further investigation into the production line.
The 68, 95, 99.7
The 68, 95, 99.7 rule tells us that about 68% of the data fall within one standard
about
deviation of the
95%
mean.
of data fall within
About
two standard
95% of
deviations
data
the mean,
fall within two standard
about
deviations of the mean,
99.7% of data
and about
fall within three standard
99.7% of data
deviations
fall
of the mean.
within three standard deviations of the
The
mean.
average height of an American adult male is
The average
5'10",
height of an American
with a
adult
standard
male is
deviation of
5'10",
3 inches.
with a standard
Using the
deviation of 3
68,
inches.
95, 99.7
Using the 68,
rule,
95,
this means that
99.7
68% of
rule,
American men
this
are
means that
5'10",
68% of
plus or
American
minus
men are
3
5'10",
inches.
plus or minus
95% of
3
American
inches.
men are 5'10",
95% of
6
American men are
inches.
5'10", plus or minus 6 inches, and 99.7% of American men are 5'10", plus or minus 9 inches.
So do you see how I came
So
up with
this
those?
means only about
The standard deviation is 3 inches, right?
Yeah.
So here's the mean. See how every standard deviation is 3 inches less.
Yeah.
3 inches less, 3 inches less. And then 3 inches more, 3 inches more, 3 inches more.
That's a sigma.
So what this tells me, yes, the standard deviation, it tells me that 68% of, what did he say, min, or height in the U.S., is that what he said? Is within 5'7" and 6'1". Okay? Then there's obviously some people that are much taller and much shorter, but that is, so when we add it up, that's a smaller portion. But when we add it to the middle, what do we get now? Yeah, see how from here to here is 95% of people in the United States? And then 3 standard deviations, which is as large as we'll ever go. That's it. I mean, that's it. 3 standard deviations is 99% of the people in the United States. So 99.7 technically percent of the people in the United States are between 5'1" and 6 foot.
So that means
about 0.3% of American men deviate more than 9 inches from the average, with 0.15% taller than 6'7" and 0.15% shorter than 5'1". This reasoning suggests that LeBron James is 1 in 2,500 and Yao Ming is 1 in 450 million. In particle physics, scientists have what are called 5 sigma results, results that are 5 standard deviations above or below the mean. A result that varies this much can signify a discovery, as it has only a 1 in 3.5 million chance that it is due to random fluctuation. In summary, standard deviation is a measure of spread. Along with the mean, the standard deviation allows us to determine whether a value is statistically significant or part of expected variation. Thanks for watching. See you next time.
This is called a dot plot. Okay? A dot plot is a type of graph that shows basically frequency. So this is kind of what I was talking about earlier with Landon. I didn't even mean to say red, but that's the same. Okay. What is the most popular color in this kindergarten classroom?
Red.
Sorry, first grade classroom. Red. What's the least popular color in this first grade classroom?
Wow.
Yeah, so a dot plot, every dot represents an observation or a poll that was taken. So I want to make a dot plot of this data here. Okay. Now data, when creating a dot plot, a lot of computer software can do it, but you need to line everything up. So for example, if I have some data that's looks like this, and I have some data that looks like this, which one looks like more?
The top one.
Yeah, but it really might not. So you need to make sure everything's lined up. So I'm going to kind of do this with you. So what is the smallest number? So these are all heights of people in inches.
Indigo.
You guys, where's our
Oh,
smallest
geez.
one?
64.
63.
63? Okay, so let's put that on the left side over here.
I found a 61. Not kidding.
And then the largest is 71.
I found a 72.
And then I believe there's one of every height. So kind of evenly split this. So 63, 64, 65, 66, and then 67, 68.
There's one of every.
68, at least one of every height.
I want to say this. What if you got 72?
Uh-oh.
Oh, what?
Oh, there's not. I wrote 72 because Cole said that. There's not.
Yeah, I was looking like, why'd you put that?
Thanks a lot.
Those people like you that I despise.
So now start putting dots on your plot to represent the data in the box. All right, so he mentioned this in the data or in the video, but what do we call data that looks like this?
Standard.
The bell
curve.
It's a bell curve. Yeah. We call this, we say, if it looks like a bell curve, we say that the data is distributed normally. So the bell curve, if data is normal or distributed normally, that means it's in the shape of a bell curve. Why do you think it's called a bell curve?
Because
It
it's a bell.
looks like a bell, yeah. Now, why do you think, in general, this is probably the most common type of distribution?
Hold on.
Why do you think lots of data, especially natural data, makes this shape? Why does this happen so often?
The average is most frequent.
Yeah, a lot of times the average is the most common, I would say, right? So think of the heights of from the video, and how many people are 8 foot tall?
Nobody.
Not very many. How many people are 2 foot tall?
A lot.
Very many.
Not very many. But how many people are 5 foot or 6 foot?
A lot.
A lot. So just naturally, you kind of see this data start to occur. We call this a bell curve. Now, real quick, before I talk about that, we already talked about this a little bit, but random sample, because now that we're kind of talking about experiments, a random sample is a subset of a statistical population in which each member of a subset has an equal probability of being chosen. So like I said, if I'm taking a random sample, but I only poll the people in the library, is that technically a random sample? No. That would be a sampling bias. So you see this all the time in politics. They'll say, oh, well, this person is leading the polls, and it makes them look really good, right? But they might have only polled, like, people in Alabama or people in Michigan, right? So this is used sometimes to influence people, which is a bad thing. But sampling bias is an error that's created in the polling due to not an actual random sample. And this obviously creates data that is skewed or flawed somehow. You can see that. So here's our normal bell curve, right? What happens the more data you take? It gets more filled in, right? And what happens if I split all these rectangles up and I took even more data? What do you think is going to happen?
That's even better.
It's going to start to get to be a real smooth curve. And a lot of that is what you'll learn in calculus, actually. In fact, this year, you start to approximate the area under a curve with rectangles. And then later in calculus, you'll find using integrals to find the exact area under a curve. But you can kind of see that happening with this normal distribution of data. So it says, sometimes data can be skewed. This is another word, skewed. Skewness, which that is a real word. Skewness is an asymmetry. What does that mean?
It's not symmetrical.
Yeah, symmetrical is like a butterfly, right? It's the same on both sides. Asymmetrical means it's not. Like maybe the butterfly got their wing cut off that day. It's not symmetrical. So when it is no longer symmetric, we call that a skew. Now, if you took a guess, see how this bell curve is kind of leaning one way?
Yeah.
Do you think this is skewed right or skewed left?
It's skewed right. It's always the opposite.
Yeah.
It is.
Ooh.
Why? Did you know that, or are you just guessing?
He's guessing.
I definitely know that. I just exactly the opposite of guessing because he always did it right.
Why do you think we would consider this to be skewed right?
Because all the lower names on the right.
All the data's to the left, which means where's the data that's throwing us off right now?
Right.
Yeah, all this. See, like if I cut this out, it would be a normal curve again. So this here, you're saying where the data is skewed. It's to the right. Or sometimes you'll see that as positively. It's where is the skewed data at? So then if you had one obviously going the other way, so maybe a bell curve that looks something like that, the data that's messed up or the data that's throwing us off is over here. So we would call that skewed left or negatively skewed. Okay. You might make a note of that real quick since I don't have that in your notes, I just have the picture. So that would be skewed right or positively skewed. And you might circle because this is the data that is causing us to be skewed. If that wasn't there, we'd be back to a nice normal distribution.
Right.
All right, I'm going to give you a 5-minute brain break.
Yes.